So, the law of conservation of momentum states that when no net external forces are acting on a system of objects, the total vector momentum of the system remains constant. Notice that the word vector is in there. Pause for cheers. In English, the momentum before is equal to the momentum after. And that, my friends, is the number one rule in this unit. The momentum before must equal the momentum after. And that includes directions. Okay? Okay, so, and here's where, this is the backstory behind, was it you guys that were asking me, or was it the grade 11 that were asking about the cartoons on the wall? I think it was the grade 11. Did you guys ask me about those? No? Okay, well, the two superheroes, they're Momentum Boy and Momentum Man. This is their origins, this particular slide. Okay, so we've got a boy and a man, and they're on rollerblades, or possibly old school 1970 roller skates, right? And so, this is before, and this is after. What is the total momentum of man and boy before? 0. How come? They're not moving, they're at rest. What is PB after? Kids would say, what's PB? Momentum Boy. And then we got talking about superheroes, and that's the origin of Momentum Boy. So what is the momentum of the boy after? Well, it would be mass boy times velocity boy, which sounds to me like a cooler superhero, Velocity Boy. What's the mass of the boy? 40. Velocity of the boy. Now it's to the left, right? So it's really minus 0.5. Right? 40 times minus 0.5 would be minus 20. Momentum man would be mass man times velocity man. Sounds like a Cheech and Chong movie. Mass man is 80. Velocity man is 0.25. And what do you know? What's the total momentum after? Shocking. 0. Momentum before equals momentum after. That's how you start every problem. Momentum before must equal the momentum after.
How would Momentum Boy be believing?
I don't know.
This Momentum Man was like
He was an afterthought.
He's a washed up. Yeah.
Maybe, yeah.
Superhero who's trying to get back in the game.
Yeah.
Yeah.
I think it was because Momentum Boy was the first one that Garrett drew for me. And then a year later he comes back with Momentum Man, so.
Oh, maybe that's in the future.
Well, I've never decided whether Momentum Boy grows up to be Momentum Man or it's a sidekick.
He comes back.
No, he's like Robin.
Uses
I don't know.
momentum to travel through time.
You guys can make a little animation for me if you want.
Oh, I know what they're doing.
Okay. Inelastic collisions. This is a word you need to know. Inelastic. Inelastic. What do you think inelastic means? Oh, and I'm supposed to have the cards for this, aren't I? We can get this in. Suppose we have two carts of equal mass traveling at the same speed but toward one another, and there is no rebound effect because they are inelastic. Because they hook together, this is an example of an inelastic collision in one dimension. Allow me to demonstrate. Can you get that rock down there for me, Connor and Jaden? Yeah. Get the whole track. Just bring it on the rear and don't hit yourself in that area. Well, I don't need that big plastic thing. That's just something people play with. That is an example of an inelastic collision. Okay? Here's the math behind it. Do you have some sort of, yeah, you're, okay. It's okay, I'm curious about what you guys have, because I always forget what you guys have. So, we're going to label them A and B. right? So if momentum of cart A is MAVA, the momentum of cart B is MBVB, but the velocities are equal but opposite signs. One is positive and one is negative. So VA is equal to minus VB. So therefore, MAVA is equal to minus MBVB, and the total momentum before is 0. That's what I'm trying to say. Total momentum before is 0. Now this is true if this is what's called an isolated system. There is no other sort of forces involved. Now would you agree, we haven't talked about kinetic energy yet, but we will in the next couple units. Do you guys know what kinetic energy is? Energy of movement, right? Would you agree that there's some kinetic energy before? Both carts are moving, right? Is there conservation of energy? Is energy always conserved? It is. So I got kinetic energy on the left, I got kinetic energy on the right, they smack together, and they're no longer moving, which means there's no more kinetic energy. So where does the energy go? Did they move up or down? No. The energy has to go somewhere. Where does it go? Not China. Good guess again. Unfortunately, wrong. Okay. Now, normally, I used to have, and someone has stolen them on me, I haven't found them. Normally, and this would be the perfect year, I really got to look for them, because Tanner, when you're done with the whiz and you got some of that magic paper left, we're going to try this. There's tons of that paper?
Yeah.
Okay, so we're going to try this when the whiz is done.
All we need is 4.
Okay, so anyways, I have these two really, it's like that flash paper that, sorry, Cat is a magician and he's going to make fire.
David Blaine.
I got these two large steel marbles that are quite heavy, and when you slam them together, you have kinetic energy, right? Where does the energy go? Come on!
Wow.
Take your hands and slam them together. Like that. What does it feel like? Do your hands feel warmer?
No.
How come? Where does the kinetic energy go? It's transformed into heat. It's transformed into heat. And you can actually start fires. What I normally do is I get some paper towel and I take the two balls and I slam them together and we get flame. And if you believe that, well,
Needs a little tiny more.
probably. Actually, what happens is, what?
You that with your hand?
And you have to have them fairly massive, and they have to be fairly smooth, and yeah, I think it'll be big mass, right? Smooth and energy efficient. What actually happens is when you slam together with a piece of paper in there, you do actually create a fire. You can't see it, but when you smell the paper after, you'll actually smell that it's burnt. So there is heat, enough heat created to make a little tiny burn hole in the paper. So with the flash paper, we should get it. I've always wanted to try this. Oh!
I thought it was only boundary.
I mean,
Oh, he's talking about the flash paper down there.
oh,
Because they took them out.
there's nothing they were fine. I don't think they would work if you like them on. I don't think you want to like that stuff. There's some nasty chemicals in them. Yeah. So I will keep looking for those big. I wish I could know who they were. Anyways, what if one cart has a bigger mass than the other? What's going to happen? Okay, so if one cart has a greater mass and the velocity remains the same, the outcome will be different. So suppose mass of A is 100 grams, mass of B is 200, velocity of A is 2, velocity B is minus 2. What's the total momentum before? Okay, so what does all this mean? PI, initial momentum, mass A, velocity A, plus mass B, velocity B. Mass of A is 100, velocity A is 2, mass B is 200, velocity B is minus 2, so you get 200 minus 400, and you get minus 200. Now, actually, this is not true because these are grams, so technically this is 200 gram meters per second, but technicality. Which means that the total momentum before is 200 kilograms. So before it's PI is minus 200, which makes PF equal to positive 200 gram meters per second. Okay? But now, what's the next question? What's the follow-up question that's going to happen here? The follow-up question is, how fast does it move? Okay? So to find the velocity of the combined system after, use this formula. PF is equal to, now what the heck does this mean here? What does M, A plus B mean? The two combined together. M, A plus B, is the mass of A plus the mass of B, which is 100 plus 200 or 300. And velocity A plus B is simply the velocity of the combined system. So PF is minus 200. The combined mass is 300. There's your overall final velocity. I'm going to do some sample ones right away. This is just kind of the theory behind it. This making sense?
Yes. Sure.
Yes? I'd like a few more nods of agreement. And don't fake it. Oh, I'm getting a distinct one from Blaine. That's good. Okay. You want to try one? How about you try this one? You're just going to have to try it on blank paper somewhere. Try this one somewhere on blank paper. I'm going to do my tens. Here's the picture, right? So here's, I got the big red ball here. It's moving at 6. The velocity of the blue ball at the start is 0. And they move a little bit slower. Did you get 4? Or do you maybe not quite know how to sort of do the math here? Don't quite know how to do the math. That's usually what happens here. Okay. So, what did I say? How do we start every single problem? Momentum before, initial momentum equals final momentum. I suggest you start every single problem like this with that. It helps focus your thinking. The initial momentum must equal the final momentum. And then you say to yourself, what makes up the initial momentum? Well, it would be the mass of A times the velocity of A plus the mass of B times the velocity of B, right? And some people like to sort of do the left-hand side first and then sort of make it work on the right-hand side. Some people like to sort of just figure out what the initial momentum is before and then say that's equal to the final momentum and sort of do it in 2 steps. There's kind of 2 or 3 different ways to do it. I'm going to do it sort of in the left side, right side format this time. So what is the mass of A? That's the red one. The mass of A is 4. The velocity of A is 6. The mass of B is 2, and the velocity of B is 0. So what is the initial momentum? 4 times 6 is 24, plus 0, 24. That's the initial momentum. It's also the final momentum. Now, here's where the subscripts and the sort of markings get a little bit weird. What makes up the final momentum? Mass of A and velocity A. No, actually, I'm wrong. All right. Because it's actually what? They're combined. It's an inelastic one, right? So it's mass of A plus B. That's right. Mass of A plus B times velocity A plus B. Okay? So your organization skills are going to be put to the test here. And your legibility skills. Because it's going to get a little crazy. So that's a B. Mass of A plus B is, A plus B is 4 plus 2 is going to be 6. The velocity of A plus B is what we're solving for. All I'm doing is just copying it down from there to there, right? How do I solve for that V? Divide both sides by 6. So it's 4 meters per second. Is it negative? No. Because it's in the same direction, Martin. But that's an excellent question.
Oh, okay.
Right? Same direction. Now, I want to talk about units here for a second. I don't sort of spend a lot of time on units, but I maybe should spend more. But what is the unit for 24? Well, this is a momentum, right? So this is going to be kilogram meters per second. But this 6 is actually just the mass, so it's 6 kilograms, right? So when you divide the units, what are you left with? Meters per second. Now, when you stop and you see it like that, is it hard? No. You just weren't sure how to do the setup, right? Absolutely. Most students have that problem. Okay. An elastic collision, then, is when there is a rebound. Okay? Trucking company called Momentum Transfer runs into a little car. What happens? Little car goes flying. Now, that's not what happens in real life because cars and trucks tend to smuck together. Okay? What if the little car bounces into the big truck? You'll notice that the big truck doesn't go very far, but the little car bounces right off. Right? It's kind of like when the little running back runs into the big lineman, right, Austin? You know what I'm talking about? Okay, so this time I will turn it around so there's no Velcro. And we'll have the big truck. Is the car at rest? No, they come together. Okay, so the big car, see how it bounces? And it goes far, right? How come? Because how much initial momentum is there before? By pushing at the same speed. Who's got more momentum? The big one, right? And so after there has to be, there's more momentum going left. So after there has to be more momentum going left, which is why the little guy goes faster that way. Okay. Total momentum before must have been the total momentum after. And when the bottom one there, when the little guy, was the truck at rest?
Taking the second
In
one.
the second one, right? Okay, so let's see if I can make that happen. Okay, this time it does that. It's going. Now I should say that perfect elastic collisions like this don't actually occur in real life because there is always some loss of kinetic energy. Okay? This type of stuff only happens at subatomic levels. They use pool table balls to sort of demonstrate it in a classroom. I don't have, oh, maybe I do. But I don't have them in a track that I can sort of make it work. So yes, the little guy should actually bounce back. But anyways, that's an elastic collision. Okay, so suppose the same two carts are involved in an elastic collision. Mass of A is 100 grams. Mass of, look, you know what? Let me just do this. I keep saying I'm going to do this. Let's just make it kilograms, 0.1 and 0.2. Oh, no, that's not going to work. Are you guys okay if it's grams? Did you notice how it can be grams? There's no constant, so we'll just leave it as grams. This time cart A is moving at 2 meters per second. B is at rest. Find the speed of cart B after the collision. Do I have something here or do I have to do it right here? No, I don't. How are we going to set this one up? Do you want to write this question down as a sample? Or do you want me just to do it? Or do you want to just watch? I've got, my next page here is this one. Do you want to just watch me do this one? How about we do that? We'll save a little time by you guys just watching me do this one. Okay, so I'm going to start it with PI is equal to PF. What makes up the momentum before? Mass A, velocity A, plus mass B times velocity B. We'll leave the right-hand side for now. Mass of A is 100 grams. Velocity A is 2. Mass of B is 200, and B is at rest, also 0. So that's going to be 200 plus 0. We have 200 gram meters per second of momentum on the left-hand side. That is going to be the same as after. Now, because it's elastic, you don't add the masses together. So how are we going to write that? We're going to write MAVA plus MBVB. But there's a problem. The problem is, This VA is before the collision, and this VA is after the collision. And they're not the same thing, are they? Right? So how am I going to make this one look different than this one? Because they got to be different variables. Well, you might want to go MAVAF for final velocity and MAVAI, but now we're starting to get a little crazy. Okay, so we'll come up with a system where we put a little apostrophe here. Okay, it's called a prime, and it is used occasionally in calculus. We'll see it. Okay, so I put a little prime there to indicate after collision. That's all it means. It doesn't have to be red. Just a little mark that says that's the after the collision one, right? Does the mass need it? Do I need to do this? No, because the mass stays the same. The mass doesn't change after the collision. Okay, so MAVA is going to be here, 100. VA is now at rest, so it is 0. Mass B, velocity B, so that's going to be 200. VB prime is what we're solving for. VB prime. This is,
Why is VA prime 0?
yeah, it should be. In a perfectly elastic collision, it should be 0. All of the momentum should be transferred.
But it bounce back.
It should, in a perfect elastic collision, it should stay 0. Yeah, I'll have to get back to you on that, exactly. 200 VB prime. 200 VB prime. So I got 200 divided by 200. VB prime is going to be 200 divided by 200, or 1 meter per second. The key thing that I wanted to show you here was how to do the before and the after, and do that prime thing. Okay, are you ready for some actual sample ones? Okay, so I got linear collision, one at rest. Linear collision, both moving same direction. Linear collision, opposite directions. Can we get 3 done, do you think, in 15 minutes? Can be close. We'll see. Regardless of what happens, you have tomorrow's period to work. Those of you going on the band trip, you might want to take a couple sheets, and maybe if it can be at a clipboard or something, you can work on the bus. I'm not saying you have to, but don't take your whole book. Okay, 4 kilogram ball moving at 4 meters per second east strikes another mass 2 kilograms at rest. At the final velocity of the 4 kilogram ball is 2 meters per second east. Find the final velocity of the smaller mass. So there's a fair bit of reading involved here, right? So it might help to draw a picture. Let's label them. The 4 kilogram ball, let's call that A. And the 2 kilogram ball, let's call that B. Okay, so let's just draw a picture here. So I got A strikes another one at rest. So this one is going like this, and B is like that. And this time it tells you the final velocity of the 4 kilogram ball is 2 meters per second. So this time it tells you that second speed Tanner was concerned about. Okay. Do you mind if I do this one a little bit different? Or do you like that PIPF left-right thing? Can I show you a little bit different way? Okay. So, I mean, it's still a good idea to say PI is equal to PF, but then just find the PI. So PI is going to be MAVA plus MBVB, and get used to writing that lots. Shane, do you have these? Yeah? Okay. And so that means the PI is the mass of A, and you have to be careful here. Like, take your time. Don't be in a rush. The A is the 4. The velocity of A is also 4. East, positive. Mass of B is at rest. So that's 2 times 0. So that's going to be 16 plus 0, or 16, and this is all kilogram meters per second. Mr. Smigalski, do you know where? Okay, so my initial momentum is 16. We're going to say, therefore, the final momentum is also 16, right? And what makes up that final momentum? MAVA. Did I tell you what we call that little apostrophe thing? Prime. So MAVA prime plus MBVB prime. Write neat. Write big. MA, mass of A is 4. Velocity A, velocity of the 4 kilogram ball after is 2. Says it right there. Mass of B is 2. Is the masses in the initial and the final always going to be the same? Yeah, and if you put it in the same order, it's going to help you, right? So I've got 2 VB prime. So I got 16 is equal to 8 plus 2 VB prime. And I'm hoping you got the math skills to solve that. You got to get rid of the 8 first. 16 minus 8, and then you're going to divide by 2, and that's going to be your VB prime. 16 minus 8 is 8 divided by 2, 4 meters per second. Okay, now, what did I do different here compared to like this kind of thing? I really did the same thing, because here I said PI is PF. I sort of did the left-hand side, right? And then I just did the right-hand side, and I set them all equal. Here I just sort of did the left-hand side separate, and then set it equal to the right-hand side, and then worked it, right? So some people like it this way. Some people like it sort of all in one here. I don't care. I can follow both. You do what you think is best for you.
But if it doesn't say the final velocity is something, is it always 0?
You'd have to assume that, yeah. Or I've made a mistake, yeah. Yes, in fact, I need to go back and I need to change this sample here, because I see that's a problem. Okay, what if they're both moving in the same direction? This one had one at rest. This one, they're both moving in the same direction. What's going to be different here? Is the setup going to be the same? I can go faster, yeah. Oh, well, will the ball go faster? You're right. But the setup is exactly the same. Do you want me to do this one the same PIP with PF kind of thing? I'll do it the same as before. I'll show you the difference. It's up to you how you want to do it. Again, A, B, this time it's 6 and 2. So that's going to be MAVA plus MVVB is equal to MAVA prime plus MBVB prime. What would happen to my grade 11? MAVA is going to be 6 times 4 plus MBVB is 2 times 3. So the only thing that's different is instead of VB being 0, it's 3.
Yes.
24 plus 6, 30. No big deal. MAVA is going to be 6. Velocity A after. A is the 6, so that's going to be 2 plus... Oh, why am I putting that? Velocity and mass B is 2. VB after is VB prime. 6 times 2 is 12 plus 2 VB prime. You can do this if you want. Minus 12 is 18, 2 VB prime, so VB prime is going to be 9 meters per second. What's different? The only thing that's different is I got a number there instead of 0. Okay?
Will it ask you to find the velocity of...
It can ask you to find velocity of anything, Ken. It's got to give you 3 out of the 4 velocities.
What about
It could possibly. Right? You have to give you all the velocities then, right? Yeah. But really, it's really just solving an equation, right? It's the setup that's new to you. Do you want to try this last one? You've got it on a yeah. You guys try this one. I'm going to put the screen on video mute. I'm going to write it out, and then you can see the answer, okay? But you guys try it. We got 5 minutes. We're good for time. Do it on the back. You would both be right. Oh, it didn't work. Or did it? -3. Did you get it? Austin, yeah? Okay, good. Yeah, awesome. Okay. So you should now be able to do the last package there. We've covered a lot in 2 days. You should now be able to do this sheet. Note that questions 1 to 7 are one-dimensional, and once you get to number 8, you'll notice that they are 2D problems. Are you afraid of 2-dimensional problems? You should be. Don't do them yet. Okay, we'll look at that next week. Okay, so you can do those. You can do the graph ones. Okay, and people that are here tomorrow will have lots of time to do that. This sheet, I had some kids once ask me for more multiple choice practice because they were having trouble with multiple choice on tests. So I found this. I have the answers to this, which I will provide at some point. So you've got some stuff to work on. Don't forget there's that hand in as well. We'll do a final hand in as well for the 1d3. That is all. Covered a lot.